Okay, Thomae's function is defined to be 0 if x is non-rational, and 1 over q if x is of the form p over q, where p and q are the lowest terms. That's a number theory thing. So the GCD or HCI is 1. Okay. Clean. P of x is continuous on 0, 1, almost everywhere. Which would make it Riemann integral, wouldn't it? Okay, so what's this thing look like? Oh, of course, if you're irrational, you're at 0. Suppose you're at a specific irrational here. Okay? Now, fix epsilon. If I can stick an interval of total width to delta down, delta up on either side of x, so that the function value is no more than epsilon away from 0, that'll show that the Thomae function is continuous at integration. Okay? Now, how am I going to do that? Well, let's examine. Let's just put a line here where epsilon. Okay. Now, the numbers, the dyadics, the n-adic numbers, but you don't actually have to do the n-adics because you get them all picked up from p-adics, right? So what I'm talking about is the multiples of 1 over 2 to the n, 1/2, 1/4, 1/8, 1/16. They're all their multiples. Let's take the multiples of 1/2. So suppose this is a kind of a microscopic thing, and 1/2 is way over here, okay? And then 1/4 is here. And then those are the closest numbers of the form 1 over 2 to the n. So let's take multiples of a quarter. So next one over here would be 1/2. Multiples of an eighth. So I'd have 1/8, 2/8, 3/8, 4/8. This really isn't very much the scale. There's 1/2. Right? 1/8, 1/4, 3/8, 1/2. All right. 1/16, 3/16. But what's the value of this function on 1/16? What happens? You know, the value at 1/2 would say would be 2, right? Or sorry, 1/2. At 1/2, it would be 1/2. At multiples of a quarter, it would be a quarter. Okay, that's a quarter. At multiples of an eighth, it would be an eighth. Remember, lowest terms.
Odd multiples.
Yeah, lowest terms.
Odd multiples of 16.
Yeah, it's getting smaller, smaller. Right. Okay, now we'll do the same thing for thirds. So at 1/3, where the hell's 1/3? There. The value of the function is 1/3, and 2/3 is 1/3. And then we do 1/5, and 1/6, then 1/7, then 1/8. Is it clear that we can find a little interval where all numbers of the form k over
Which one?
I want to get rid of them all.
Q over Q in the end.
A set of numbers, P over Q, where Q is greater than the greatest integer in 1 over epsilon, is finite. Thank you. Is it not? So I take 1 over epsilon. I go find the greatest integer in 1 over epsilon, and then I look at the Q's that are bigger. So what does this mean? It means 1 over Q is less than epsilon, right? Oh, heck, I don't even need the greatest integer function. How about this? It's understood here that Q is an integer and epsilon can be anything. So it's true that 1 over Q is less than epsilon. Well, P can be anything. That's a finite set, right? At least in 0, 1. Intersect this in 0, 1. It's not a finite set unless I intersect it with something like 0, 1. Okay. There's only finitely many of those things. Where Q is a small number, is what I'm saying. So after a while, Q gets to be a pretty big number. But that's good because then 1 over Q is a small number, maybe less than epsilon. I can arrange it that way by insisting that Q be greater than 1 epsilon. It's a finite set. So fine, I go find them all, and I say, certainly X isn't one of them because it's irrational. And then I look for them all, and I pull my horns in until I can make a symmetric interval around X that excludes all these other ones. Okay? All right. So, what's the variation of the function on this little interval now where I found my delta?
It's double
Was it a bug crawl?
Okay, we'll come back to the monotone thing. You see that now we're inside, we're away from all these finite set where 1 over Q is greater than epsilon. And that shows that this is continuous, and it's continuous at an irrational. Why is it discontinuous and irrational? Because at irrational is 1 over Q. If the rational is P over Q, the function is 1 over Q. So pick epsilon equal to 1 over 2Q. Okay. So can you surround the rational with a little delta interval, plus minus delta, such that the variation of the function is less than 1 over 2Q? No, you can't, because it's 1 over Q in the middle, and it's 0 to either side, right? We lost her. She's gone. Oh.
I don't think it was systematic, but also
It's irrational, or it's your rational. And the denominator is Q and it's continuous, and we find it jump ball.
Well, but
So you can always specify epsilon smaller than that.
yeah, but you also have the density of the irrationals and the reals.
So you make your epsilon.
So it's even worse. You always drop down to 0. Arbitrarily close to a rational, you have an x where f of x is 0. that blows it out of the water. You have not met the epsilon condition, so it's. But since it's countable, you can surround each one with an epsilon interval, epsilon squared, maximum epsilon cubed, add them up like you do, and it has measure zero, which means this weird function is Riemann interval by the base term, even though the discontinuities are dense, right? In any interval, there's a discontinuity because there's a rational there. It seems weird to me, but it's true. Okay, they wanted to see the monotone. Let's see if I can explain this. I made myself some notes. So first, that's this two